Okay, so in this video we'll be talking about the theory behind particle kinematics, so the motion of a point or the collection of mass all compressed to a single point here. Both generally, so we'll be talking about position, velocity, and acceleration, and then moving into how those things relate and how we can express it and analyze situations where the motion is in a straight line. And that brings us to kind of the introduction to chapter 13 in the book. We'll start here with section 13.1 if you're following along, right? And kind of just introduce ourselves to position and how we define it. Okay, so this is defined relative to the origin of our chosen coordinate system. Okay, so let's put our coordinate system here. I'll draw mine as a typical Cartesian coordinate system. So this is typically Cartesian, right? So what I mean by that is x, y, and z. It's a kind of a good way to think about it here at the start. But this could easily be, and we will get into, polar coordinates, cylindrical coordinates, curvilinear coordinates, which is the most general. Okay, and now let's say we have the motion of some particle, right? Just some point moving in space, maybe a mass or the center of mass of an actual object. Okay, this is the actual path kind of flowing through our chosen coordinate system. It's chosen in terms of that's going to make it a convenient choice for our analysis. Okay, let's see. Let's use P for the point of interest, and then we have a vector going from the origin to that point P. Position vector is going to be R. Okay, so let's put this here. P is in motion, so that's why I drew my vector here as, well, I denoted it as a function of time by writing the little function of time thing, right? So this is our position vector. And there's a lot of things going on here, right? But most importantly, right, this is, well, it defines the position. So in this case, it would define the x, y, z coordinates, and those are going to be the components of the vector there. But more importantly, it's from the chosen origin, right? The chosen origin of the coordinate system that we chose for analysis of this system. Okay, meaning that this one is not. Could change if you go to a different coordinate system. It definitely will. Wait, just translating the coordinate system somewhere, the origin of the coordinate system somewhere else. Okay, let's define now velocity. Since this is in motion, we're going to need to do a few things to our diagram, and we'll keep referring back to this here. But later on here, right? So after some, this is going to be finite time or discrete time later on. We'll have a new position for point P, right? So this would be P, later on. And this is going to be at a time later on denoted by a delta t later. Okay, so our definition of velocity, right, is then going to be, start with the actual definition, right, which is the change in position through time. And how we've done that is we've let this delta t, change in time from one position to the next, go to 0. And then we have the change in position. And that's a vector quantity divided by the change in time. Okay. Now this numerator here is it's a difference between two vectors, and we have those two vectors on our diagram, right? So it's that one minus r of t. So it's really, that vector, that arrow subtracted off. And so we're subtracting off the blue arrows I've drawn it, right? So from vector addition, or in this case it would be vector subtraction, what we actually have there, the numerator is that vector right up there. So this is a delta r. And that's also it's also a vector, right? So let's make some observations based on that, right? So what we're actually doing here, is defining delta r to be that numerator. Okay, and then as our change in time goes to 0, our delta r, and then following naturally from the definition up above there, our v vector become tangent to the path, to the green line there, right? So as delta, as our time becomes smaller and smaller, the second p here becomes closer and closer to the original p, and then this delta r vector just points right along the tangent to the path at that point. Okay, a few things about notation. We could have easily, we're going to choose to write this as time derivatives with a dot over the top, right? So that's just a definition of d dt, right? Derivative in time. Yeah, that's it, right? So let's just put this time derivative notation. Right, a lot of times you'll see spatial derivatives with a prime, right? And so time derivatives is the one we're going to see, a lot. Okay, let's then, right, the third big component to kinematics, discussing motion without talking about the forces that cause that motion. All right, the third big component is acceleration. Acceleration then, well, if velocity is change in position over time, acceleration is then change in velocity over time. Notationally could be v dot, and since v is r dot, r double dot. So acceleration is the second derivative with time of position, or the first derivative of time with of velocity. Okay, we got some good definitions there. Oh yeah, and I like to always box the important definitions, or when we get to important results, or the final result of a example problem, or when they're working through any problem, right? I want to make one note here. And that is when I said about position vector, right? So the position vector is going to depend on our choice of a coordinate system, or at least where that origin is of the coordinate system. And you can imagine if we chose down here, right, that's going to be a much different position. Or maybe we would choose the actual, this position to be the origin of the coordinate system. Well, then, the coordinates there would just all be 0. So position vector does depend. But once we've gone to a time derivative, right, and it's just a subtraction of two, the numerator, and so therefore the direction of our velocity vector is just the difference between two position vectors. That doesn't matter, right, depending on where the origin is. So as long as it's the same type of coordinate system. So another way to say that, right, is that our velocity and acceleration of a point, so in this case, right, that's p, these are so let's see here, are the same relative to any fixed point. So right now the one important fixed point is the origin, but we could then choose a different point to be kind of the point in which we're taking, as the fixed point in our coordinate system. Oh, I already wrote that. In the chosen reference frame. Okay, so this is the first time we're seeing this word reference frame. We've already used coordinate system. So let's have a discussion about reference frame here. And I've used the word chosen again, right? So all these things, when you choose a coordinate system, when you choose a reference frame, oftentimes, right, we're trying to make a nice convenient choice for the analysis that's to come. And oftentimes you make, one choice and it's the wrong choice, right? It didn't make life easier when it came to analysis. And so we need to rework through, under different assumptions. Okay, but a reference frame, right? Let's say there's somebody down here on, well, some planet, but probably planet Earth. And then we got a plane flying overhead. Let's see if I can do this. Not too embarrassing here. Okay, that's pretty good so far. Ooh, it's starting to look more like a cartoon. Oh, it looks almost like a flying marine animal of some kind. Okay, so this is meant to be like a plane that's then, you know, soaring through the sky and could be accelerating with respect to the fixed Earth, right? Or at least as this reference frame, it would be fixed compared to that reference frame. So let's say we got a person there, and we've got a person up here, and maybe there's a person. I mean, these maybe aren't standing outside of the plane, but they're actually on the plane, and maybe they're tossing a ball to one another. Okay, so let's then write the velocity of the plane. Now this is the velocity of the plane with respect to the ground, right? The separate reference frames. We have reference frame A down here, and then maybe this is the reference frame BC because persons B and C are up there, right? So the reference frame A, the velocity of this reference frame with respect to the fixed, you know, the other reference frame A is given by this capital V, and then the ball itself has maybe a lowercase v, and that's going to be a vector as well. So lowercase v of t, and so this statement down in this diagram here, what we're saying here is that the velocity of the ball is the same relative to B and C, but it's going to be different for A. And we will get into what it actually is. I mean, there's no surprise. A is just going to see the balls moving with this velocity plus that velocity, right? And they're vectors, so there's actually a vector addition going on. But so this velocity of the ball with respect to B and C is lowercase v of t, and down here for A is going to be this movement of the plane's reference frame plus that one. Okay, so that's an important distinction here, and that's going to be the same for acceleration as well, right? Because it itself is a time derivative. If you're sitting in a particular reference frame, it doesn't matter whether we choose B as kind of the fixed point in order to do analysis, or C as a fixed point for analysis. Okay, so now let's move on and start talking about now applying these ideas of position, velocity, and acceleration to a particular, kind of the most trivial type of motion, rectilinear motion. So what we mean by that, rectilinear motion is going to be movement in a straight line, maybe 1D motion, and see how we would analyze situations like that. Okay, so conveniently, we're going to choose the origin, O, and a coordinate, S, that is along this 1D path. All right, so by definition of this type of motion, rectilinear motion, it's just moving along in 1D. So it's like a one-dimensional number line. Now, it might not be horizontal as you observe it, or as any observer in a reference frame would, but no matter what, by definition of rectilinear motion, there's motion only in 1D. So it can only move this way. The particle can move that way or that way, and it's set. All right. So based on that, we'll just conveniently choose that direction to be the S coordinate. The origin is just somewhere on it. Maybe there's a reason why we choose that. And let's say at a particular instant in time, the particle of interest is sitting there. Yeah? Okay. So let's notice one thing here. Well, so first of all, right, our position vector is defined to be from the origin to our particle P. Okay, so let's see. R of t is the vector position, but because we're limited to staying on this number line where s is a coordinate, kind of like an x, right? Kind of like an x value as we see it here, right? So as you move along, it's going to take on different s values. So the s value is going to be higher here than it is here, and it's actually going to be negative s values this way, if I guess we choose that to be our positive s direction, right? So r of t, which is a vector, right, is a position vector, but it's fully described by the scalar position. So we have vector position r of t, the scalar position s, meaning if I tell you s, you can then back your way to knowing exactly what the actual vector is. Okay, so this is because the direction never changes. Okay, and what we mean by that is we are always moving in that direction. All right, so because we're always moving in this direction, wouldn't it be convenient to then just have a unit vector, right? So meaning the magnitude that, right? So the magnitude of this, you know, e of e with the hat on top, you know, well, the magnitude is always 1, meaning we're not storing the information of our point P in terms of its magnitude, you know, magnitude of r of t in the unit vector. Instead, we're just storing the direction. And because it can only move in that direction, no matter where P is, it's always going to have that direction, right? So instead, we store the information of the magnitude of r to get to P, wherever it is in time, into the s coordinate. And then E hat is always the direction, okay? So we choose this E hat as the unit vector. Oh, went off the screen there, sorry. E hat as the unit vector in that direction. And that is parallel to the path. Okay, so let's see, unit vector, what we mean by that is the magnitude is 1. And so we're not storing any of the magnitude of the position vector. Okay, so our position vector is fully described by the s coordinate and this unit vector that's not changing. Magnitude of r, direction of r. Yeah? Okay. So that's good. Now this is like how we would then represent our position vector in this, you know, first shot at a particular type of kinematic motion. Now let's, can we then do the same thing for velocity? All right. Wouldn't that be convenient? Well, yes. Let's see. V, our velocity vector, is defined to be dr dt, which, well, what is dr dt? Well, E is always the direction of r and doesn't change in time. So we can pull that out, and then we'll just have the only thing that can change in time is the s coordinate, right? As P moves, you know, left and right, wherever it goes, maybe it's accelerating, has some velocity, changing its position. The only thing that changes to its position is the s coordinate. So we have ds dt always pointing in the E direction, or E hat direction. And okay, well look, right, might as well, to follow in line with here, let's just call this scalar velocity v. Okay? So we have v, E, and then we can say, well, the scalar velocity is then defined to be just the change in time of our scalar position s. Okay, so let's make up a position. Now this is going to be, well, with a little bit of thinking, not too complicated of a plot, but it's a little bit weird, right? So this is a position s in time, where s, remember, is kind of our horizontal movement on our 1D path as we drew it up here, right? So what we're actually doing is we're taking this coordinate and flipping on its side, and then down here we're having like where that position is in time, right? So what its s coordinate is in time. Let's draw maybe a made up, right? This could go anywhere. As long as we're always marching forward in time, we can't go backwards in time. We'd break physics there. But we can definitely go backwards in s, right? Go backwards in space, but not in time. Okay, so if we then pick a particular time to analyze, right? And this is where we said, you know, the slope or we get a tangent line, our change in position vector. Well, we get it here with the scalar quantity as well too. All right, so if we at this point take a tangent line, able to calculate its slope, right? So for a unit time change, what is the change in s? That is your velocity, right? Slope of the line tangent to the position curve, and in this case, a scalar position curve. S of t, that's your scalar position curve, at time t is our scalar velocity, v of t. Great. Okay. Well, then we got one more step, which is to look at the scalar acceleration, right? And just as we're able to quickly go from velocity to if the velocity is the derivative of the velocity vector is the derivative in time of the position vector, which led to, for the rectilinear motion, the scalar velocity being the time derivative of scalar position. Well, then because vector acceleration is the time derivative of the velocity vector, we get the same thing here, right? Where the scalar acceleration is a time derivative of the scalar velocity. And what we mean by scalar, right, means that there's no direction associated. It's not actually a vector, only a magnitude, right? And this is just exact same derivation here, except put a here and put v there, and everything else falls out naturally. Right? dv dt in the e hat direction equals some definition of what a is. A is our scalar acceleration. Yeah. Okay, we could do this something similar here. We'll do it a bit quicker here. So I'm not going to use, blue was reserved for maybe a position. Oh, no, I'm sorry. This is velocity. So associated with this, maybe we try to match it up. I kind of shifted it off to the side, but right. So here, this is going to be a positive velocity. Oh, yeah. Let's try to do that. So at this point in time, there's a positive velocity, kind of getting close to 0, but then increasing a little bit. So it kind of goes like this, and then it goes higher, and then as we get to that point right there, we cross over the -0 line, -0 velocity, but stay pretty close, negative only for a tiny bit, until we shoot back up, right? So I'm just trying to represent the slope of this line, where I've kind of matched that point right there, right? That's the one point I know for sure. Okay. Regardless, we have just some. Now, if we go to this, maybe we'll try to match this point again. That's going to be somewhere. Well, I think so. This starts out really low. Actually, let's try to keep it accurate. Maybe that's like the starting point. Starts pretty small and then steadily gets steeper and then turns over. So maybe it look more something like that. Maybe that's not there. Okay, not important, right? But regardless, this is going to be a point where we have a pretty high, well, not the highest velocity. The highest velocity would be right about there before it turns over. But somewhere around here, right? Maybe it's kind of steadily increasing here. This now, the slope of that, which I've kind of drawn pretty not sloped very well, right, is going to be the acceleration. Okay, so we could make a very similar statement to what we did up here. The slope of the line tangent to our velocity curve v of t at time t is a of t. Okay. Now there's one thing we're going to be using a lot, right? So these are all now, now we have relations from one to the next, but these all involve time as well. Meaning, the velocity is a change in position with time. The acceleration is a change in velocity with time. You could actually work your way back that the acceleration is also the second derivative of position with time. You can also use the chain rule to do something important here that we'll see showing up time and time again, right? So if acceleration is dv dt, okay, but v, all v is or sorry, so let's say v is a function of position instead of time, right? So if we express velocity as a function of position instead of time, so dv ds, so if we know what our s location is, and then that defines what v is, well, we can take this, right? So it's a change in velocity with the s coordinate. All right, well, ds dt is just v. And I should say, we haven't made anything up here, right? This is just a chain rule. dv ds ds dt, that's completely fine, just another way to define it depending on how the relationships work out, right? So this kind of thing here, so let me a equaling v dv ds is going to be something that we will use often in our analysis. Okay. All right, so let's then, what types of kinematics can we do, right? And so I just got done saying, hey, well, another way to express it. You're like, well, why would we have to do this, right? And I know we're going through the theory here nice and slowly. But let's now talk practically. What types of problems are we going to see for this rectilinear motion, all right? And so in general, our types of kinematics problems are as follows. Okay, we could have acceleration specified, and this is why I've tried to be careful with the language I've used, which is to say, when v is a function of s, it's not like the world just has imposed that, or the universe has imposed that. It's really just a choice. Have we chosen to express velocity as position? Was it a convenient choice? But regardless, when we enter a problem, if we can say, well, acceleration is specified as a function of time, or it's going to be, that's kind of the information we have about the system, we're going to start with that type of a problem, right? In other situations, acceleration is going to be specified as a constant. That's like gravity. We could have situations where acceleration is a function of velocity and acceleration is a function of position. Okay, and these first two are covered in sections 13.2 and these last two are found in sections 13.3. Okay. Okay, so we're going to take these one by one then, and develop relationships with acceleration specified in these different ways. What does that say about velocity and position? Okay. And how those things change in time, if acceleration is defined in these different ways or specified in these different ways. Okay, so starting with situation where acceleration specified as function of time. Okay, and I should also say, right, if that's the case, B, when we get to there, right, B is going to be a special case of any of the others, right? Because if acceleration is constant, well, that's a constant in time. What does that mean about the functions of velocity and position? So you should always be able to back your way into B here from the others. But I'll mention it when we get there. Hopefully, I'll remember. Okay, so first thing we got to do here is determine velocity. From the specified acceleration as a function of time. Okay, so we'll go back to our relationship, right? And now keep in mind, right, this right-hand side is the thing that is specified, so we can use that, right? If we see that in our final relationship, that's fine. So we're going to take this exact relationship, And really, part of the practice here is kind of solving these, differential equations in a way, right? Differential relationships. There's derivatives involved. And so how do we do that, right? We want to unwrap the dv dt. Well, in order to do that, we need to take an integral in time, okay? And from some initial time, usually 0, but it could be some initial time to some time t, all right? So then we have to do the same thing to the other side. Well, whenever we have this relationship, right, dv dt times dt, right, this is an infinitesimal change in velocity due to an infinitesimal change in time, right, really division there, and then we're multiplying that by an infinitesimal change in time. Well, all we're going to get is that infinitesimal change in velocity. This is dv all by itself, right? And it looks like we're just canceling dt and canceling them out. They really are, but remember these are infinitesimal, so there is an issue in limits as the change in time goes to 0. But they do really cancel, just like a fraction would in this case. Okay, but if we ever do that, now we have dv. Well, that means now we're going to write the velocity at the original time. So our integration variable is now velocity, right? And so I'm trying to be really careful with this right at the start here, right? What we're saying here is this is the velocity at time t equals 0, and this is the velocity at time t. Okay? So the right-hand side then doesn't really change at all. I'll just put it in black. And just remember, this is specified. A of t, the acceleration is specified. So we can integrate it and do that. That's part of the work, right? Okay. And this, maybe here, this is initial velocity, you might say. And this is general. If we're doing this completely general, this doesn't need to be the initial time. It could actually be the thing you're trying to solve for is down here. Maybe you know the velocity later on in time, right? But in general, usually we'd write it like, maybe this is not in general. For the cases we see most often, let's say, right, we now have the velocity in time is going to be some initial velocity plus the integration of acceleration through time, right? I should also say, like, I'm not being too careful. I'm not going to be too careful as we go forward either, of like having a ghost variable or a pseudo variable inside here, right? So like we're reusing time here, but really when you do the integration, this variable should go away, because we're we're looking to write this as keep it as a function of time. The notation is there, what I'm going to use, right? Okay, and then the next, now that we have this, right, so this is kind of a good final result. It's completely solvable now, right? We don't have a form for the acceleration, but if we did, we could now plug it in. Okay, and then let's go down to position. Okay, for that, we'll start with the definition that velocity is change in position through time. We'll do the same thing here, so I'm just going to, can I fit it in there? Maybe I can fit it in here, right? So we're going to do a dt to get rid of position. We want to solve for position and time from some initial time to some final time. Do the same operation to the other side, so we're not breaking any mathematical rules. The next step, right, well, is to realize, well, this is just ds. We then have integration from s naught to s, where this is our initial position, right? ds t0 to t v of t dt. This is our s at time 0, or initial position. Okay, and finally, well, gotta sneak it in here because I'm actually running out of my page here. S of t is the initial position, right? That just comes from this side. This will just be s as a function of time minus s naught. Pull that to the other side. And now that we have our way, again, a of t is specified, we can integrate that once, get what v of t is, and we have the ability. We would need to go to a specific problem. We have the ability now to solve for position as a function of time. The other thing that needs to be specified are our initial position and initial velocities, right? Okay. Great. So let's now move on to case B, which maybe have these up here for just a second, right, is going to be a special scenario here, right? If a of t is a constant, right, this is a very trivial integral, right? It'll just be that constant acceleration times the change in time. Well, if that's the case, then this is now linear with time. When we integrate the velocity linear in time, we should get a quadratic relationship down here. Okay, and we'll work through the details now, but no, right? We expect to see linear velocity, quadratic position, if acceleration is constant. Acceleration is, if acceleration itself is quadratic in time, right, this then raises up the order 1 to a cubic, and this raises up the order here to a quadratic, right, as you take an integral. Okay. So that is what I labeled as case B. Acceleration specified as constant. Special case of A. So we got some nice examples here, right? The one is gravity, or at least gravity if it's isolated, first of all, and also constant acceleration due to gravity. So we're close to the Earth, on Earth's surface, meaning basically the gravitational acceleration is constant. As you get further away, or as you get more massive, as the object gets more massive compared to Earth, we can no longer make that assumption, right? But this is the case where acceleration is specified as a constant. Okay, so then we go to, because this is a special case of A, part A is what I mean there, right? We can then use that result and just plug in the constant A. Well, we'll put A naught there, just to differentiate it from A as a function of time, because it's not a function of time here, right? Do the quick integral, which is a trivial one, like I said, and we get t minus t naught. Okay, this is our velocity whenever we have constant acceleration. So one thing we need to remember as we move along here, we get all these different relationships. What assumptions did we make to derive this result, right? So this is not a general result. This is only the case where acceleration is constant. We can't be using that in any other scenario but that. It will lead to incorrect results. All right, once we have that, this now is slightly more complicated. We're plugging in v into our position relationship, which requires an integral. Okay, this v naught, well, that's just going to be v naught times t, but then we'll just have the difference in our two bounds, t minus t naught. And this term over here, right, t minus t naught, well, that, we can integrate that as the integration variable here. So what we get is t minus t naught squared. Okay, this is our position, again, only for scenarios where we have constant acceleration. Great. Now here's where that alternate way to write acceleration comes into play here. So often it's more convenient, or based on the inputs and the things you want to know, the knowns and the unknown, it's going to be more convenient to have a relationship to express velocity as a function of position. All right, so we have up above here is what the velocity is as a function of time. We have what position is as a function of time. We don't have what velocity is a function of position, but we should be able to. I mean, think of these as like a parametric representation of two different functions, right? So recall, we already derived this from the chain rule, that A can be rewritten as that, all right, which not just dv dt, but this now is how v changes with position. Okay, so if we start from that, we say v dv ds equals, now because this is specified, right? Specified. Maybe even go back up to here, right? This is the thing that is specified for this case, which is why we had to make these statements about our final results. Not general, because we started with this assumption, right? That's the thing that's specified. We'll specify it again down here, and I didn't leave myself enough space here. But now we do this integral, right? To get rid of the dv/ds, we need to integrate in space position. Do the same thing to the left and the right. Right. Well, now this combination is just our differential change in velocity from those two positions, and we can then convert this to a velocity integral, and this stays as a position integral of that constant acceleration. Okay, well, v dv, that's just going to go to v squared over 2 minus v naught squared over 2, and that equals a naught s minus s naught. Or, solve this for velocity. Velocity at time t, and maybe we just keep the square on this side, is equal to v naught squared plus 2a naught s, where s is a function of time, remember, as well, s minus s naught. Okay, this is the result for velocity versus position, not as written as a function of time, for the constant acceleration case. Don't try to use this in any other, well, when you can't justify a claim that acceleration is constant. Okay, great. So we're done with the two A and B. Remember, the other two are just going to be more extensions of this. So we'll just kind of work through those a bit quicker here, since we now have the mechanisms for how to solve these. Remember, now we're moving into section 13.3 if you want a reference to the book, right? But this, the next scenario is where acceleration is specified as a function of velocity. And now this one we might not have experience with, but this is going to be the case where, like if you have drag, so drag on a plane, drag on a car, right? So anything that's kind of the faster you go, well, it turns out that the resulting effect on acceleration depends on, typically velocity squared. If you have like a really viscous fluid, like you drop like a ball in like corn syrup or something like that, you can, or something that's really viscous, like a really viscous honey, the actual effect, so you drop it, and so there's gravity pulling it down, but the actual effect of the actual fluid itself has a where acceleration goes as a velocity. So the faster you go, the deceleration goes as velocity. Right? And so we're kind of specifying that if I know the velocity, I will know what the resulting acceleration is due to this physical effect or whatever. So maybe we also have movement through a viscous fluid, something that's really honey-like, doesn't flow too easily or naturally. Okay, so we'll start with analyzing velocity as we've done. dv dt defined to be a, but now a is a function of velocity. That's the thing that's specified, so any result we get isn't only going to be valid for this scenario. Okay, so again, I didn't leave myself enough space. Oh, here we actually have to rearrange this, right? We need to get all of the, well, what we want to do is we're going to have to integrate this in time. Okay, but I did leave myself enough space here because, well, if you could look here, right, this is going to be a function of velocity, or that'll be an integration in velocity. So we need all of the functions of velocity over to this other side, which means we need to pull that on over, right? And then all that would be left over here is just going to be 1. Do the same integration to this side. Okay, no cheating there, right? We just first divided by the acceleration just to get all the velocity variables to the left-hand side, and then an integration of both sides with time from initial time to final time, or whatever time you're looking to analyze for. And now we kind of have to like leave it here on the left-hand side because we need, in order to do anything more, we would need to plug in what this function was. But we integrate this from v0 to v, and this is a function of time, right? So that's the thing we're actually looking to solve for, is up there in the upper bound, t minus t0. Okay, so this is kind of, you know, unsatisfying because we don't actually get to a final result. But you can imagine if you specified this, you actually were given, you know, acceleration as v squared, you could actually plug in 1 over v squared, take the integral, you know, subtract off the lower bound, plug in the upper bound, and there is your velocity. You can actually solve for velocity as a function of time. Okay. So solve left-hand side for v of t. Okay, and then position is actually we've already done this. If you have v of t now, this is exactly the same as case A. Once v of t is known, we can then go to what we've already derived. That position as a function of time is just initial position. Integrate velocity through time. Nothing new here, as before, case A. All right. Great. One more to get through here, which is, and then the next time in a follow-up video here, we'll have a bunch of examples of this. Acceleration specified as function of position. Okay. We've been talking about some examples. What are some examples of this one? What gravity actually is, right? So we often say, well, gravity is acceleration due to gravity is constant. Well, that's only because the small changes in position when we're near the Earth's surface of this really massive planet compared to like the objects we deal with means that we can it's basically constant. But gravity actually depends on how far away we are, or how far the two objects are apart from one another. So gravity actually acts in this scenario. So if you're using the true the universal definition of gravity, magnets act like this. So the acceleration due to, you know, two different magnets. Springs, right? So objects attached to springs. The further two springs are, or the further that the spring is stretched or compressed. So basically, the distance from its equilibrium position tells you what's the resulting acceleration going to be through the force that's, you know, provided by the spring. Okay, so those are just some examples. Regardless, it would need to be specified. Again, here we're just focusing on description of the motion, not actually the forces, but it's kind of a good idea to keep an eye on what types of forces we're talking about for each individual case. Okay, as always, we start with this definition of how acceleration relates to velocity, but here now acceleration is a function of position, so that is what's specified. Here again we'll use this alternate way to write expression so that we can, you know, we don't have any information about time here. We only have information about how acceleration changes with space. So we need to rewrite this left-hand side in terms of a spatial derivative. Okay, so we'll take v dv ds. That equals to a of s, giving ourselves lots of space to fit in here, that now we want to take an integral in space. Take the same integral operation to the right-hand side that we did to the left-hand side. Okay, and this is again where we leave it. I guess the only thing that we can change here is that this is dv, so we convert this to an integral. And this right-hand side doesn't have anything changed at all. Okay. Yeah, so we could just then say solve this well, this left-hand side we can actually do something with, right? Because this is, yeah, let me actually rewrite this. This is v squared over 2. So you could say this is v squared over 2 equals v naught squared over 2 plus s naught s a of s ds. Okay, where this is actually, maybe, let's be really careful. This is a position, a function of position. Okay. To then actually get to what our position is through time, right? We take this relationship, as always. I don't know if I'm going to be able to sneak this in here. Since we now have, well, okay, we're going to rewrite this relationship. I'm actually going to pull everything to, we're going to divide by v of s, and then integrate through time, and we'll see what happens there. This is just like what we've done in the past here, where we're looking to integrate, we're looking to get, we only have v as a function of s, so we need to get this as an integral in s. But that's going to come through by an integral in time first. Okay, so we divided by 1 over v to both sides, so on the left-hand side originally is just going to be unity, 1, and then we switch the order here. But this allows us to write this as a spatial integral, right? So in the end, it'll look something like this, where again it's not going to be, this one we can't actually solve, but the thing we're solving for is up there in the upper bound of our integral, 1 over v of s ds equals t minus t naught. Okay, and then we need to solve the left-hand side here. Solve left-hand side for s of t. Okay, great. We worked through all the theory here for the initial sections in chapter 13. Again, this is all for rectilinear motion, so purely motion on a single 1D number line, essentially, along a constant coordinate here. There'll be a follow-up video here with plenty of examples, and the focus here was working through the general relationships for the individual cases, and we'll work through problems going forward on each of the individual cases. All right.